claims that
Sorry. Yes.
yes, yes, sir. He gives a short introduction. He says it'll use only elementary calculus, and that the deepest result you need will be the mean value theorem. So,
Okay.
and with being an algebra book, like there's surprisingly little algebra in this in
Yeah,
this proof,
that's
but
hmm.
that's to be expected because its definition is from analysis. So yeah.
Right. Right.
Anyway, so the number E is transcendental. So his notation is f, same notation, ith derivative of f with respect to x. This
That's
uh,
fine.
and then he says, so suppose that f is a polynomial of degree r, where r is of course we can assume it to be a whole number in general, but that is not relevant, with real coefficients.
Hmm.
So and then he introduces this capital F. He just sets it to be this.
Right.
So f of x plus first derivative of f plus second derivative and so on up to fr,
Hmm.
r derivative. And from r plus 1 onwards, the derivative is 0 anyway. So that is not included. So he stops it at fr of x.
Hmm.
So now he says we compute the derivative of e power minus x f of x.
Yeah. Again, due to some cancellation, again it comes out to be this. Right. Yeah.
Yes,
E power
yes, yes,
minus small fx.
yes.
Right.
It
Again,
comes out to
the
be,
product rule and cancellation. Right. Okay.
yeah. So since again he uses this, since f is of degree r and the basic property of E. So
Hmm.
this property of E, uh, I guess the one could say that this property of E is what is pinning down the transcendence of it. Uh, but
Okay.
it makes sense because E is the only number that has this property. So of course, so it makes sense.
Right.
So he computes the derivative of this new function e power minus x f of x, and it
That's
comes out
what.
to be this.
Yeah. Right.
And now he introduces the mean value theorem. So if G is continuously differentiable and a single valued function defined on this
Right.
closed
We know the
interval,
mean
that
value theorem. This is the mean value theorem. Right.
yes, yes. So this is just the mean value theorem,
Right.
where he has introduced this theta. I mean,
Yeah. And the linear right.
but I guess that makes sense. I mean,
Yeah. Yeah.
it's easy to see why it, yeah. So now he says we apply this to e power minus x f of x, which is continuously differentiable, definitely, and it is single valued, and it is defined for any real number. So it's of course defined for whatever closed interval you take. Uh, so
Right.
he takes 0 to k, where k is any positive integer. That is
Hmm.
his closed interval. So it includes 0 and k and every real number in between. Now, now he applies the mean value theorem and he obtains this. So e power minus k f of k minus f of 0. So that is this
Yeah.
uh,
That is.
numerator.
Yeah.
And then this this comes out, this
K
comes
is
out,
the
this comes
difference.
from here. Yeah, k is the difference. So that is why this is here. And then he applies the derivative, which we know, and it comes out to be this, where theta k depends on k and is some real number between 0 and 1. So I suppose this is clear as well so far.
Correct. Yeah.
Then he multiplies throughout by e power k, and he obtains this relation in general, which is valid for any positive integer k, 1, 2, 3, or so on.
Well, that is just.
So
Yeah.
then,
That's fine. Yeah.
yeah. So then he says, he writes out, he just makes it more explicit.
For
F of
every k
1
you
minus
write
e.
it. Yeah.
Yeah. And he calls these numbers epsilon 1, epsilon 2, epsilon n, and so on. So
Hmm.
this is our definition for epsilon,
Hmm.
epsilon I, where I is between 1 and n. Then he
Right.
says, suppose that E is algebraic, then it is the root of some polynomial with integer coefficients.
By
Just
definition.
by definition, yeah, where all these are integers and C naught is greater than 0. I don't know how, like, I don't know how he claims that, but
No, you can just
I don't.
multiply by minus 1 if it is less than 0.
Oh, okay.
Right.
Yeah. So okay, so he takes C naught to be greater than 0, and everything else is an integer.
Mhm.
So in the relation, so from what we have here for epsilon, he multiplies the first equation by C1, second by C2, and so on, and then adds them up.
Exactly. Right. And one of them becomes
Right.
0. Yeah.
One of them
By
becomes
2.
zero because E satisfies this relation.
Hmm.
So it's very nice. Okay, so that happens. And so
Mhm.
adding these up, you get this
Yeah.
plus f of 0. He takes this f of 0 common, you get 0. So you
Right.
just get C1, epsilon 1, C2, epsilon 2, and so on up to Cn epsilon n.
Right.
So in uh okay. So this won't be 0 actually. This will be minus C naught.
Yeah, that's right. And then we are done, right? Because now we will get that this E, this 1 E squared T to the N, that's has a relation,
Yes.
linearly dependent. But then the proof is done because this shows that Q at joint E is a finite dimensional vector space.
Yes.
Because
And
if
then yeah.
Right, because if you have e to the power n plus 1, then that can be written using these smaller powers by using this last equation that you have arrived at. This is equal to minus c naught. If you use this equation, then you can write any higher power of e higher than n in terms of these lower powers, right? So q at joint e, uh, that can be written, that's a finite dimensional vector space, and that means, yeah, but let's see what happens after that.
Yeah.
Sorry, I mean, the proof is
He
not done
hasn't
because, yeah, we only get that.
he hasn't taken that approach.
He has not taken that
Like
approach, right?
no,
Because that approach
no
does not
algebra
work.
involved.
What I said doesn't make sense actually, because it just shows that it's algebraic. Means, uh, okay, so what I should say is the following, which will simplify the thing a little bit. When you are assuming that E is algebraic, okay, then from some general theory, you get that Q adjoint E is a finite dimensional vector space. Okay, that over
Hmm.
Q, that actually shows that this kind of relation will exist. So you don't have to go through these things. Okay, I mean,
Oh,
if you are not going to use what the CIs are, then you really do not, means this equation 2, na, this actually directly comes, right? So you
right.
don't,
Yeah.
but I think, so I mean, yeah, you're right, because then you won't have this capital F thing. Yeah, maybe I should not say anything because actually I don't know what he's going to do. No, it's more tricky than I was thinking. Yeah, sorry.
And sir, can you see my screen? Something happened. I think the
No,
power
no,
went or
I can see your screen. Yeah, it's fine.
okay. Okay. So he just combines the relations. So he this part is equal to this part. So you get
Huh.
this.
Right. Yeah. So about the epsilons,
Uh,
you are getting some relation. Okay.
yeah, about the epsilon. Yeah. And now, so since f was constructed from some arbitrary polynomial f, it should hold for every polynomial with real coefficients. And
Right.
so he chooses a very specific one, and he says it was first used by Hermite. This one,
Right. Okay.
where p is any prime number, but the thing is p has to be large. So
Ah.
since there are infinity prime numbers, we
Yeah.
can always choose some p greater than n and p greater than c naught. So
Okay.
he says take p to be a prime number satisfying these two and define this polynomial in terms of p.
Hmm.
Uh, yeah, again, n is clear what it is. It is the degree of the equation. And p, we just discussed what that is. C naught is clear.
Right.
So now he says we will take a look at the values f of 0, f of 1, all the way up to f of n, and then estimate the size of epsilon 1, epsilon 2, and so on.
For this f. Okay,
Yeah, for this f.
correct. Okay.
So when expanded, f is a polynomial of the form this. So again, p minus 1 factorial being in the denominator is obvious. So is
Mm-hmm.
x power p minus 1, x power p and all that. But the important fact is that the a naught, a1, these are all integers. But I guess that follows. Again, just expand this out and you can see that it follows.
Yes.
Right, yeah. This is definitely a polynomial with integer coefficients. They're very easy to see.
Right. So why are you getting this n factorial from?
Oh, the
Right.
n
Yeah, I
factorial.
get it. Yeah. Yeah.
Yes, yes.
Because you have to pick constants from other factors.
From other
I
factors,
mean,
yes.
constants, and the constants are 1, 2, 3, so you get n factorial.
And then collect
To the
them for x bar.
right. Nice. Okay.
Yes, yes. So where a naught, a1, and so on are integers. So when I is greater than or equal to p, we claim that f, the ith derivative of f at x is a polynomial, which is true. The derivative of a polynomial is a polynomial. But the important thing is coefficients are all integers which are multiples of p. So he has not given a proof of this, but he says see problem 2. So this is what we have to show.
Mm-hmm. No,
So
but that is obvious
since I've
because
been
when you take the derivatives, I mean, if you take p derivatives, you get p factorial in the coefficient, and that
p
cancels with the p
factorial, yes,
minus 1. Yeah.
yes.
And
So
that's how
that
it
is
also
done.
becomes divisible by p. Right. That's fine.
Yeah.
Yeah. Next.
So this just makes it a bit more clear. But here he
Yeah.
says where I lost it. No, okay,
Yeah.
here. So thus for any integer j, fi of j for I greater than or equal to p is an integer and is a multiple of p.
Yeah,
The
because it's
coefficients
integer
are all
coefficient.
multiples of p.
Right.
So you add them up, it is definitely divisible by p.
Perfect.
Now, now from its very definition, f of x has a root of multiplicity p at x equal to 1, 2, and so on. That is
Yes.
just
Yes.
very clear here.
Yes.
Nothing to see there. And at
Mm.
0, it has a multiplicity of p minus 1, I suppose. Yeah,
Right. Yeah. Yeah.
right.
Yeah. Correct.
So from multiplicity, we know that f of 0 should be f of 1 and so on all the way up to f of p minus 2. That is just the multiplicity for polynomials.
Right. Yes. Exactly.
F of 0, he has computed it to be 0. Uh,
Mm.
that
Yeah.
is easy to see. We'll
Yes.
have 1 to n factorial here, but a 0 over here, so it comes out to be 0. And hence all the derivatives up to p minus 2, up to the p
Yeah.
minus 2th
Because
derivative
it's a
must be
multiplicity.
0.
Yeah.
Yeah, multiplicity of p minus 1.
Yeah.
Oh, okay. Oh, I skipped something. Okay, my bad. Okay. So for j equal to 1 to n, we have fj of 0, f1 of 0, and so on. So that again, because of this 1 minus x, 2 minus x, n minus
Yeah,
x.
but small f and capital F have the same roots. So the same thing will hold for capital F also.
Yes.
But sorry, yeah, capital F is not a polynomial. Yeah.
Yeah. No, it is a polynomial.
It is? Okay.
Yes, so capital F is defined as a sum of
Oh,
all
okay,
these.
okay. I thought it was E thing. Okay, cool.
No. It's uh right. So for j 1 to n, f of j is 0. That is clear to see. And
Mm-hmm.
hence f1 of j is 0. Fp minus 1 of j is also 0. Here we're
Mm.
taking p minus 1 because these numbers they have
Multiplicity P.
they are multiplicity p as opposed to p minus 1. So f of j is this. And by the
Yes.
discussion above, fj is an integer and is a multiple of p because they're equal.
Yes. Ah, because they are
Right.
equal.
So yeah.
Ah,
So
okay. What is the
Now
R?
he looks at
What is the R?
R is the degree of the Hermite polynomial. This R is R is this. F is a polynomial with degree R.
Sorry.
So in
Got it. Yeah.
R will be P my this
Right.
degree something. I
Yes.
really don't know.
No, that's fine. That is okay. It is some NP plus P minus 1. Yeah.
Yeah, something like that. Yeah.
Yeah. But then you see
Right,
this
right.
capital F of J. Can you scroll there? Yeah, capital FJ.
Yes,
This is an integer because each of these FJs are integers.
yes, yes,
Is
yes.
that the reason? Because they are not all equal.
Yes, yes, yeah. It is an integer and it is a multiple of P. What?
Multiple.
Oh,
Yeah, but
for
it
1
is
to n they are equal.
for 1 to n P, 1 to P, they are equal. Beyond that, they are not equal, but still its fact remains true because of the previous paragraph.
Yes, yes.
Right.
Fj is an integer and is a multiple of
Multiple
P.
of P. Okay.
Now we
Nice.
come to f of 0, where what I discussed previously.
Hmm.
Now for I greater than or equal to P, fi, the I derivative of f of 0, it's an integer which is a multiple of P, which we know, that we know. But
Right.
the P minus 1th derivative of 0 is n factorial to the power P. That we have to come back to this for that.
Hmm.
So all these,
Mm-hmm.
since they're higher order, and we are taking, so the x will remain.
Huh.
But from here,
And
the P
here it will be only
factorial
there, and that P minus 1 factorial will
come
cancel out.
back down. Yeah, so that will cancel out with this P minus 1 factorial, and here we'll have n factorial to the power P remaining.
Okay. Okay. Fine.
So that is there. So n factorial to the power P, and since P is greater than n and is a prime number, of course P doesn't divide n factorial to the power P. P doesn't divide n factorial, so it cannot divide n factorial to the power. Well, no,
Mm-hmm.
I shouldn't say it like that, but it's easy to see why P
Yeah,
doesn't
that's
divide
fine.
this.
Yeah.
N is smaller than P. We have specifically chosen P to be so
Larger
that P
than.
doesn't divide. Yeah.
So now we have
So
something which is not divisible, and so for capital F of
yeah,
0 also, it will not be divisible.
not be divisible because everything else is divisible.
Right.
Right.
Exactly. This is the only one which is not divisible. Right.
Yeah.
By P. Okay.
So f of 0 is this whole thing.
Hmm.
So we conclude that f of 0, it is an integer but not divisible by P.
But what about this small f pth derivative at 0? Is this divisible by, how is it divisible by P?
P's derivative of 0.
Is
Yes,
it
sir.
divisible by P or not?
Oh, okay, okay, one second.
Yeah, it is divisible by P. Because the other terms, the other monomials, they will all accumulate a P, right? So it's divisible by P.
Okay, okay, right, right,
And
right.
the first
Yes,
one
yes.
will, and it's important that the others are divisible by P so that we only have one guy. We only have this one term which is not divisible, so the sum is not divisible.
Yeah. So
Fine.
this one, this is
Yeah,
the
that's the
only thing.
important one.
Right. So because C naught is greater than 0 and P is greater than C naught, and because P doesn't divide f of 0, but P divides f of 1, f of 2, and so on. So
Okay.
now they take an integer combination, C naught f of 0, C1 f of 0, and so on. But see this thing, C naught, P is greater than C naught, so it definitely cannot divide this. That we know.
Mm-hmm. Yeah, and it divides the other
But
ones.
it divides everything else from the
Yeah,
discussion before.
right. And how are these C's
So
chosen? These C's are those C's for the E, for the
these C's,
polynomial of E. These C's.
these are the
Cool. Yeah, these are the
this one.
C's. Right, right, right.
So now he takes this. So we have come to the conclusion that this thing, this entire expression is an integer, but not divisible by p.
Perfect. Okay.
But we know that it is equal to this.
Now we are back to the okay.
Right. Now epsilon I is this. So what he has done, he has just gone back to the definition and plugged in, theta1 for f. But
For the
now we're
Hermite
using this
polynomial.
for
Why? Okay.
the Hermite.
Okay.
So he gets this, where theta
Hmm.
I is 0, greater than 0, less than 1. So now he takes the modulus, or it must be, okay, he comes to this conclusion. So then e to the power n power p, n by p minus 1 factorial.
Mm-hmm. So how is that happening?
Right.
So these theta i's are less than 1. So you can use that.
Right. Theta is less than 1. So, hmm. Okay. So, yeah, okay. I think, yeah, that only he used. So,
Right.
uh, so if theta I is less than 1, then so is I theta I.
I
If
is a complex
0,
number, right? Or no?
no, I is the index. So,
Ah, I'm sorry. Yeah. Okay.
yeah.
Okay. Okay.
So
Yeah. So
0,
then it is done because this I is less
I.
than n. So this
Yeah.
power may I theta I, this will be less than n. So that part is e to the power n part is done. And
E
similarly,
to
the
the
other
power,
parts, right?
right.
But no. But how are the others?
N power p is done. I think,
Yeah. This n power p is coming from the last term,
yeah.
last
And
factor, and in the middle, every term is less than n factorial.
right.
No, it is less than n
Okay.
factorial, right? Because it is this thing to the power this. It is this thing, 1 minus theta I. But why is that less than? Hmm.
So we know that I theta I is greater than 0 but less than I. So
So it is
minus I
just.
theta I
Yes.
is
It's
big,
fine. It's fine. This is just this 1 minus. So you look at this 1 minus I theta I,
the
then
1
2
minus I
minus I
theta
theta I, 3 minus I, and n minus I theta I, that is less than n
I
factorial.
will be less
Right.
than n
And then
factor.
power
Yeah.
of that to the p is less than n factorial to the power p. So yeah, then it's
Yes,
fine.
yes.
Yeah, it's a cool thing. Yeah.
Right. So he has made this observation.
Okay.
E power n p and to the power times n factorial to the power p by p minus 1 factorial. So this whole thing. But
Right.
now p is a prime number and he makes p
Yeah,
arbitrarily large.
it goes to 0, right? Yeah. And exponentials, and
So
here it
it
is factorial.
here, yeah, below it's
N is
factorial,
fixed.
there
So
it's
n is fixed. So there's
and
nothing to worry about.
n is fixed. So yeah. So this is again, so we can sort of see even a similar sort of thing was used for pi, where a power n by n was
Yeah,
used.
that's right. I mean, that was that that was the Fourier coefficient. It is why it is going to 0. But anyways,
Oh,
we can talk. Yeah, it's a Fourier coefficient of some good function, so it has to go to 0. Otherwise, some
right,
summation will not converge. Yeah, but it's the same reason
right,
actually. Yeah. Okay.
right. So
Yes.
now we can find a prime number larger than both C naught and n, which is large enough to force this. So he says this
Ah,
must be true. But so we will come back to that. But C1 is equal to this, so it must be an integer. So it is
right.
smaller than 1. So our only possible conclusion is that this whole thing is equal to 0.
Mm-hmm. Right. Got it. And but it is not
But
divisible by p. Yeah.
but this implies that this is 0. But p
Mm.
divides 0. Everything divides 0. So this is a contradiction.
No, p does not divide 0. Oh, yeah, right. P
P does
divides
not
0.
divide 0,
P
but
P
p
divides
divides
0.
0.
P does not divide this. I'm sorry. Yeah.
Yeah.
Okay.
So we're getting P divides 0 and P does not divide 0, so which is contradiction.
Yeah.
And hence E must be transcendental.
This is a more difficult proof, right?
Yeah,
Than that
definitely.
one. Yeah, it's
Yeah. But pi, that was only irrational. Irrationality for E is, I would say, easier than the
yeah,
pi.
that is easy because that is just some
Yeah,
division. Yeah. But
right. So
so this one is less than one because this is this product. Can you scroll up maybe?
that is because of this.
Hmm.
So
Each of the
since this
coefficients are going
term,
to zero. Right.
they are going to 0, so we can just take some P to be. We can force this. We can see that. That is,
Right.
but just from the definition of the limit, also we can just see this. We
Yes.
make each of these like smaller than 1/n. We're done. We're done.
Right. Cool. Yeah. Nice.
So this proves
Yeah,
E
that was
must be
very nice, right? We should
right.
appreciate that. That was very nice.
And in the problems, he has given prove that he is
Yeah,
irrational.
this
Then
is
lemma, and he has given this as well. This exact same one.
yeah, those things are fine. Those things is just fine. There are two things. I mean, the earlier thing which you said, this x to the power n, 1 minus x to the power n, that you should look at because that is what is the beta distribution.
Which one, sir?
This x to the power n times 1 minus x to the, in the previous proof, sorry, I
Okay,
should
okay.
say, yeah, that polynomial is to the beta function. There's a gamma function, right? And that polynomial
Right.
leads to the beta function. Okay. And
So I
it
suppose
is
there
the
is some
there has to,
motivation.
yes, there has, yeah, means at least that time when Niven found the proof, he did it maybe directly, but now the language of that's some 1947, I suppose, right? Yeah, but now it's
Yes,
yeah.
yes.
So that thing is now used in beta distribution. You can check it what it means. It's beta density is a density function. Means you have to
Okay.
normalize it, then it's a density function, and when you integrate it, that helps you to calculate probabilities. Okay. And
Right.
so that
I've
might be a
heard of
motive.
beta and gamma. Gamma I've
Yeah,
heard.
gamma distribution, and this is a beta distribution. So if you look at it, you will
Right.
find it's
Is
very,
this
very
the
important. Right.
Wikipedia page?
Yeah. So with some yeah, exactly. So if you look at this one,
Oh,
right. So this you have to consider this division to normalize. Okay. Why do you
oh,
normalize? You normalize so that the integral is one, and integral is one is
yeah.
like saying the
You
probability.
want it to be
It can be treated
probably
as a
every.
uh,
Yeah.
right, and then it is very much connected. I mean, right now we don't have the time, but it is very much connected with these probabilities of Bernoulli distribution and things like that. Okay. So maybe you can look
Right.
at it and see if you find some motivation through this. Okay. But beta distribution is like very essential to studying probability and so on. Okay. So that's one thing. And the
Right.
second thing is that this thing which you consider, this fn sine x. Okay. So you see also that this function x 1 minus x, that's like it takes values -1 and 1, it takes equal values, right? So
Which
and
one?
that's that function which you considered, x to the power n times 1 minus x to the power n, it takes equal values at
So X
-1
and
and 1. Sorry,
-1 and 1.
it takes 0 value, right? Sorry, 0 and 1, I'm sorry, yeah,
Yeah, 0 and 1. Yes.
at 0 and 1, right? So you can continue it periodically on the right and on the left. It is as you can continue it as a period one function,
Right. Right. Yes.
right, on the whole real line. So you can think of it as a periodic function, and then there is a theory of Fourier expansion. So you would want to expand this function in terms of powers of e, and the coefficients that you get are precisely that fn sine pi x integral 0 to
FN
pi.
sin phi.
That is precisely that
Right.
thing. So that expression is a Fourier coefficient plus cos part also. So maybe instead of sine, you can write it to the power I pi x, and then
Oh,
that coefficient has to go to 0 because that coefficient is going to be the nth term of a convergence series, which is a Fourier expansion. Okay, which converges because the function is a very nice function. Okay,
okay.
so
Right.
that has to go to 0. So that is not a problem. But this of course by no means provides a motivation to the proof. But maybe there are
Okay.
some links. I do not know. Yeah, maybe you should ask some of your professors in your college, because you have, I
Right,
mean, not us, but you have actively read it. So I suppose you should
right, yes.
ask and see. Maybe some number theory people are there, then they can, right?
Yeah. Oh, and so I have a friend at ISI. So
Hmm.
he actually got a notification to come to Azim Premji to come correct RMO papers.
Okay.
So he might be coming here. So on I think November 6th or something, the papers will come here and
Uh,
they'll have to correct. And my professor said he'll like ask to see if I can join in as well, like for the
yeah,
correction process.
that will be, of course. I mean, correcting a paper is supposed very nice, because
Yes.
yeah, it's in retrospect you learn to write better also, maybe. I don't
Right, right.
know.
So I'll get there's 30 qualified from Karnataka.
Okay.
So, and I think there'll be like, I guess 20 volunteers. So we'll have to correct maybe like 2 papers each.
Okay. But that is
Uh,
that's will be nice, and you can also probably have already solved the problems of RMOs, tried them
right,
this
yes, yeah, it's quite easy,
this
but
time.
yeah.
Okay, okay, right. So that is okay. And
So they
yeah,
will be
there are,
coming here.
but about this, talk to the people. Okay, and
Yeah,
this,
yeah, yes, yes.
because there should be some better proof. I mean, because you're already like uh, reading all these things, and yeah,
Right.
maybe I don't know how it will connect up. Yeah. So is your college also an RMO center, or
No, no, it wasn't a center. Like they didn't write it here. But
but the
since the both coordinators are from here, like for
okay.
Karnataka, so that's why they're correcting it
So who
here,
are
I
they?
suppose.
If I know them,
Uh, Sir, one coordinator is Doctor. I'll just show you the picture.
okay, you can type their name. Okay, there is
Uh,
the list
like
of.
this has like a profile and all. Yeah.
Yeah, maybe.